The recent 12-day war between Iran and Israel from a year ago offered a rare glimpse of the world's most advanced air defense systems facing a much cheaper and less sophisticated ballistic missile force. The outcome surprised many observers. A significant number of ballistic missiles penetrated American and Israeli defenses, causing considerable damage despite their limited accuracy. Reports suggest Israel expended roughly 30 to 40% of its Arrow 3 interceptors, while the United States used around 15% of its global THAAD interceptor inventory and even deployed SM-3 interceptors from destroyers in the Mediterranean. That amounts to years of production and billions of dollars consumed in just 12 days of fighting. It's speculated that the rapid depletion of interceptor stockpiles may even have been one major factor behind Israel's decision to bring the conflict to an end. If an advanced missile system defense struggled under those conditions, the challenge becomes even greater when the target is an intercontinental ballistic missile traveling at Mach 25. To understand why, we first need to look at the defenses currently in service, and you'll get why the Golden Dome proposed by the Trump administration is very likely to fail. To intercept an intercontinental ballistic missile, defense networks only have 3 windows of opportunity. The longest of these is the midcourse phase, where the warhead coasts through the vacuum of space for roughly 20 to 30 minutes. To counter this, some nations rely on systems like the Ground-Based Midcourse Defense, or GMD, or Naval Aegis BMD. They detect the launch, calculate the orbital trajectory, and then fire an interceptor into space. In control tests, these systems perform well with a good success rate, and it's definitely due to the fact that the intercept trajectories are calculated in advance, with clearly identified targets and predictable launch windows. A real nuclear exchange, however, bears little resemblance to these conditions. A modern ICBM, such as the Chinese DF-41 or the American Minuteman III, carries multiple independently targetable re-entry vehicles, or MIRVs, alongside hundreds of countermeasures. The challenge for a defense system is telling the fake ones from the actual warhead, which is very hard, by the way. The problem for the defense system lies in the aerodynamic drag equation. FD equals 1/2 rho v squared CD A. In this equation, rho represents the density of the fluid the object is traveling through. In the vacuum of space, rho is exactly 0. Because atmospheric density is 0, drag is 0. This means Newton's laws of motion apply uniformly to objects regardless of their mass. A 500-kilogram thermonuclear core and a 20-gram mylar balloon shaped like a warhead will travel at the exact same velocity and follow the exact same orbital trajectory. An attacker can deploy a cloud of hundreds of radar-reflective balloons and heated flares. To the infrared sensor of an incoming kill vehicle closing in at 10 kilometers per second, like a balloon lightly heated by a lithium battery, is almost indistinguishable from a true warhead. The kill vehicle has milliseconds to calculate which of the several thermal blurs on its sensor is the real target in order to fire the thrusters. This is not an engineering problem. It is a fundamental limitation of physics. A defense system designed to intercept a single warhead is easily overwhelmed by cheap countermeasures. If the defense network fails in space, the final opportunity, which is less of an opportunity, is the terminal phase, the last 30 to 60 seconds of flight where the warhead re-enters the Earth's atmosphere. This is where systems like THAAD and the Russian S-500 should come into play. Intercepting an ICBM within the atmosphere is a huge problem due to the vehicle's kinetic energy and maneuverability. The kinetic energy of an object is defined by the equation EK equals 1/2 mv squared. Because velocity is squared, an incoming warhead dropping from the exosphere at Mach 25 possesses a huge amount of kinetic energy alongside massive potential energy from its altitude. Conversely, a ground-based interceptor must launch from 0 velocity, fight gravity, and push through the thickest parts of the lower atmosphere to reach the target. In any interception, the object with the higher energy state has a huge advantage. Modern ICBMs compound this advantage by utilizing maneuverable re-entry vehicles, or MARVs. If a warhead traveling at Mach 25 alters its course by just a few degrees, the ground-based interceptor must expend massive amounts of its own fuel to adjust its intercept geometry. Because the interceptor is fighting atmospheric drag while flying upwards, it's at a huge disadvantage. The word hypersonic has become a geopolitical buzzword, largely referring to new hypersonic glide vehicles like Russia's Avangard. But the reality is that an ICBM from the 1970s is already a hypersonic weapon. Defense systems are already incapable of intercepting normal ballistic warheads in the terminal phase due to the sheer kinetic energy involved. A hypersonic glide vehicle simply takes the already insoluble problem and extends its duration by keeping the weapon in the upper atmosphere longer. We still struggle to stop the weapons we have faced for 50 years, so the introduction of glide vehicles is not really that significant. The offense will always win regardless. Because terminal interception requires fighting gravity and mid-course interception is blinded by zero-drag decoys, defense strategists frequently propose intercepting the missile during the boost phase. During the first 3 minutes of flight, the ICBM is a massive, slow-moving rocket filled with highly volatile fuel, and it has not yet deployed its decoys. Because ground-based interceptors are geographically too far away to catch a missile launching from deep within Siberia or central China, defense contractors routinely revive the concept of space-based interceptors, a network of armed satellites in low Earth orbit, originally popularized during the 1980s Star Wars Brilliant Pebbles program. While theoretically sound on paper, orbital mechanics don't really favor this concept. By applying Kepler's laws of planetary motion, we know that a satellite in low Earth orbit must maintain a velocity of roughly 7.8 kilometers per second to avoid falling back to Earth. Satellites cannot hover. Therefore, a single interceptor satellite is only positioned over a hostile launch silo for a few minutes before it simply moves on. To guarantee continuous coverage over a massive landmass like Siberia, you would need a constellation of hundreds, if not thousands, of satellites. Yet the mathematics of these orbital tracks reveal a severe inefficiency. Because the entire constellation must constantly circle the globe, only a tiny fraction of the network will be geographically aligned over the launch site at the exact moment of an attack. Furthermore, intercepting a boosting ICBM from space requires the satellite to aggressively alter its orbit to reach the target. This requires a massive expenditure of propellant governed by the Tsiolkovsky rocket equation, delta V equals VE log m over F mo. To achieve the necessary change in velocity, or delta V, to intercept a boosting ICBM within a strict 3-minute window, the satellite requires an enormous mass fraction of propellant. And this makes the whole idea even more unviable. Launching hundreds of massive, fuel-heavy interceptors into space is prohibitively expensive. If an adversary launches a simultaneous salvo of just 10 ICBMs, the handful of satellites properly positioned in orbit would be exhausted in just a moment. The vast majority of the multi-billion-dollar constellation remains on the wrong side of the planet, rendering the entire defensive network useless. With kinetic missiles constrained by gravity, the Tsiolkovsky equation, and sheer cost, the defense industry frequently points to directed energy weapons, specifically high-energy lasers, as the ultimate solution. Lasers travel at the speed of light, effectively eliminating the maneuvering advantages of the ICBM. However, relying on lasers for ballistic missile defense ignores the physical laws of optics and thermodynamics. History already proved this with the cancellation of the YAL-1 airborne laser program. The concept was straightforward: mount a megawatt-class chemical laser on a modified Boeing 747 and destroy ballistic missiles during their boost phase. Although the system achieved several successful test intercepts under carefully controlled conditions, it proved impractical as an operational weapon. First, lasers are subject to the inverse square law. I equals P over 4 pi r squared. As the beam travels through the atmosphere, the intensity, I, of the laser decreases proportionally to the square of the distance from the source. A megawatt-class laser that is lethal at 10 kilometers loses its destructive irradiance long before it reaches a warhead at 50 kilometers. But the biggest problem is thermal shielding. A laser destroys a target through thermal ablation, heating the material until it suffers structural failure. This requires the laser to hold its focal point on the target for several seconds, a metric known as dwell time. An ICBM warhead is a machine explicitly engineered to survive the most extreme thermal environment on the planet. During atmospheric re-entry, the air compressing in front of the warhead generates a plasma shockwave with temperatures exceeding 3,000 degrees Celsius. To survive this, the warhead is encased in an ablative heat shield, designed to burn away and carry thermal energy off into the slipstream. Trying to destroy a re-entry vehicle with a thermal laser is the equivalent of trying to melt a volcano with a magnifying glass. The laser is utterly useless and pointless in such a scenario. Taken together, the limitations of boost, mid-course, and terminal phase interception point to the same conclusion. Missile defense is constrained less by engineering than by the economics of the offense. Every improvement in missile defense demands substantial increases in cost and complexity, while the offense can add complexity far more cheaply than the defense can overcome it. For a defense system to work, it must correctly identify the real warhead, ignore the decoys, perfectly calculate the orbital mechanics, and successfully execute a collision. It must do this flawlessly every single time. For the offense to win, they do not need to invent new solutions. They simply need to manufacture more Mylar balloons. An adversary can build 10 cheap dummy ICBMs and 100 radar decoys for the price of a single advanced interceptor missile. The cost-exchange ratio favors the attacker. This is ultimately why hypersonic missiles don't matter in the grand strategic calculus. The panic over hypersonic glide vehicles is a distraction from the uncomfortable reality that we are already entirely incapable of stopping the ballistic missiles that have existed for 50 years. The physics of interception are too demanding, and the economics of defense are too fragile. Accepting this reality is what led to the doctrine of mutually assured destruction. We do not rely on interceptors to protect us. We rely on the undeniable guarantee of retaliation. The only working defense against a weapon that cannot be stopped is ensuring that it is never fired in the first place.